So that is about all that I have. Are there any questions about the nonlinear stuff or about anything in the whole presentation? Okay, so I have to be honest with you. All of the current books about solvers are for solvers people. And by that I mean the following. I can recommend some very good books about solvers, but they're really about the mathematics of solvers, the implementation details, that type of thing. And so if you're curious about the solvers themselves, they're good. But there are no books. I want to write one, I guess. There are no books that are this character of user's manual. How to go out, how to pick the right solver, that kind of stuff. How to make it a little better, how to optimize it. There's really nothing there. And the best things tend to be the descriptions by people in their papers of what they're using. So the first thing I would recommend to you really is to read the Pilot JGR paper, which has a pretty careful description with a lot of references for the solvers that we use. If you really want descriptions of solvers, there's a free book online by Yusuf Saad, S-A-A-D, and it's free and it's great. That's what I learned them out of, and so it describes most of these. But I would go to the JGR paper because its orientation is this is how you go about assessing and optimizing the solver, and that's really, I think, the useful way of doing it. So, Brad, there is some time. Oh, go ahead. Yeah. So there is some time left. Brad, what did you run last time when there was a little time left? Do you remember? Oh, I know. You ran the TET4 example with because you could do solvers on a larger problem. So we could do that. We could run that example if people would like to see solver behavior for a larger problem or something like that. We could talk about more general questions or something like that of formulation. I'm not sure.
Yeah, so
we could
20 minutes here. We have just one more session in the Schedule B that I think hopefully there'll be some time at the end. It's going to be mostly about running in parallel and sort of issues involved in running in parallel and how to make the sort of the best use of Pilot related to sort of other optimizations that you can do in terms of choices between different components. So if you have general questions about how you want to, how do you want to go from here to your research problem, or just very general questions about Pilot features, we have some time right now that this is a good opportunity. We have Matt, Charles, and I all here to try and answer your questions.
be a long question.
Cases of static or quasi-static problems do we need?
Oh. Maybe that's a math question.
Okay, so let me try to answer that. So let's start. Okay, so suppose the problem is static. Okay, first with no faults. A static problem with no faults is just elasticity, and then algebraic multigrid will do a really good job, and there's no reason to worry about anything. If you put in faults, which I gather you would, because it's not interesting unless you do, typically, then you start to deal with the saddle problem. And you will probably be fine on converging the bulk elastic problem, and the problems will arise on the convergence of the subproblem for the tractions, or the other piece of the problem for the tractions. These are very easy to monitor. You can see how the elastic problem is converging. You can see how the traction problem is converging. And so it's not necessarily a matter of doing sensitivity tests. I mean, these solvers slowly degrade. So they just slowly get slower as you make the problem bigger. So there's no tipping point or anything like that. It's just that it might be slower than you want, and then you start fiddling with the tolerances. If you're running on a bigger parallel machine, you might start changing the solver to get fewer inner products. So I think the thing to be aware of is, as you increase problem size, how are the number of iterates in the linear solve, or the sub-pieces of the linear solve, how are they tracking, and how is the time tracking? So that's how I do it. It's just, 3 or 4 numbers, and you look at this line and you say, is that the line I want to be seeing? Normally you want it to be flat.
The only thing I would add to that is that for the solver tolerances, that is something where you do want to get an idea of the sensitivity. Because you can, if you're trying to go for 10 to the minus 20 when you can get away with 10 to the minus 8 in terms of relative tolerance or absolute tolerance, then, you're going to be saving yourself a lot of runtime. So, you need to be looking at sort of your data and your sensitivity to the solution relative to what your observations are, to figure out what solver tolerance is going to work. When we use 10 to the minus 8, we're probably a little overkill for the relative tolerance and our just the quasi-static, no nonlinear.
Yeah, I mean, fault friction is still a little, still a little tough, because, you really want a kind of higher level formulation, and we're still working that out. Okay, the combination of elastic with viscoelastic layers. Not really, because the way that Pilot is set up, the changes in the elastic moduli line up with the mesh, and as long as you mesh in the jumps in elastic coefficient, algebraic multigrid does great. Where it's not so great, where it can degrade a little, is if you have sort of smoothly varying coefficients that sort of have a jump in the middle of an element boundary or something like that. But we don't have any of that. So as far as I know, the algebraic multigrid is going to be good. If you can find a case where it doesn't work, that would actually be great for us, because then we could maybe publish it. Oh, no, not yet. I guess that's one thing I'd like to. When we add those to the distribution, I will try to put a little description at the top, just like Brad does for the step configuration files. But it pretty much tracks my notes for the slides. So basically, you want to use Solver 3 for your initial investigations, and then for scaling up, you want to start with Solver 7. The other ones are just for examples. So you want to always start off with something like Solver 3, which is an exact solution, and then when your problems get bigger, you want to move to something like Solver 7. You start out with that.
Any other questions?
So it seems like we're about done with questions now.
Yeah, is that it?
So final call for questions.
Well,